Hello everyone. Welcome to our competency-based question series designed chapter-wise to strengthen your conceptual learning and understanding. So let's start with problem 1 of chapter 4, moving charges in magnetism. It says a stream of singly charged particles having mass m1, it is accelerated through a potential difference V and is projected into a uniform magnetic field B1 that is equal to 0.2 Tesla. So this is your charged particle having mass m1, and it follows a circular path to reach the detector at this point. Another similar charged particles, but with different mass, m2, are again subjected to the same potential V and are made to pass through the magnetic field B, but it fails to reach the detector. We need to find out by how much value the magnetic field should be changed, or by how much value the magnetic field should be applied so that this particle having mass m2 should strike the detector. So let's try to solve this problem. And a very basic understanding is that if m2 will follow the same radius that is followed by m1, then the charged particles will reach the detector. So we need to find out some relation of magnetic field with the radius r so that both the radiuses can be equal, and then we can move ahead. So let's try to solve this problem. It says that the charged particles are accelerated through a potential difference V. So the kinetic energy of the particle is given as Q into capital V. Q is the charge of the charged particles and V is the accelerating potential through which they are accelerated. So half mv square, where V is the velocity of the charged particles and m is the mass, that must be equal to Q into V. And from this, we can say that small v, it is equal to Q capital V with a multiplication of 2 divided by m having an under root. So okay, small v, that is the velocity of the charged particle, it is under root of 2Q capital V by m. This is our equation number 1. Now, there must be some relation of the radius with the magnetic field. So we know whenever a charged particle it moves in some circular path, it has some centripetal force, and this centripetal force, it is given by the magnetic Lorentz force, that is FB, force due to the force on the charged particle when it moves through a magnetic field. So here I can write the centripetal force that is equal to mv square by r, that is equal to qv capital V sine theta, the magnetic Lorentz force. This theta, it is equal to 90 degree, since the charged particles are moving in this direction and the magnetic field is coming out of the plane of the paper. So the charged particles have a velocity in the direction v I cap, and the magnetic field is having a direction k cap coming out of the plane of the paper. The angle between them is 90 degree, sine 90 is 1. So we can write mv square by r is equal to qvb. This v gets cancelled out with this v, and we are left with capital B is equal to mv by rq. Now put the value of v that we've obtained in equation number 1 in this equation and try to find a relation between b and r. So this implies capital B is equal to 1 by r m by q multiplied by 2q capital V by m under root. And when you solve it out, this m is having power half. It will cancel this m, and this m is having power 1. It will cancel this m. So we get B is equal to 1 by r under root 2 m capital V by q. So this is the relation between B and r. Now we know that the radius for both the charged particles having mass m1 and m2 must be equal to r in order to have the same trajectory, so that the charge particle with mass m2 also strikes the detector here. So let B1 is the magnetic field for the charge particles with mass m1. So we can write 1 by r under root 2m1 capital V by q. For charge particles with mass m2, we can write B2 must be the magnetic field for the radius r only, so that it strikes the detector. 2 m2 capital V by q. When I divide B1 with B2, I get m1 by m2 under root. So this is something we got. And from the question, we can see that this m1, it is 4 times m2. It is 0.8 into 10 to the power minus 26, and m2 is 0.2 into 10 to the power minus 26. So we can write this that m1, it is equal to 4 times m2. Using the relation in the above equation, b1 upon b2, it is equal to under root of 4 times m2 divided by m2. m2 gets cancelled out with m2, and we are left with b1 by b2 is equal to 2. This implies b2 must be equal to b1 by 2. Let's check the value of b1. So b1 is the magnetic field for the charge with mass m1. It is given to us as 0.2 Tesla. We can put the value of b1 here. b2 is equal to 0.2 divided by 2, and it will come out to be 0.1 Tesla. That is the required answer. So in order to have a radius that hits the detector for the charge particle with mass m2, we have to apply a magnetic field equal to 0.1 Tesla. Thank you very much. Keep learning, keep practicing, keep excelling.